Dear learners, in today's video we are going to dive into a very important concept of crystallography and X-ray diffraction, that is atomic scattering factor. So we are beginning with the simple cubic unit cell. Now when the X-ray falls on this structure, it gets diffracted from the atoms present in the unit cell. And if we zoom into one of the atom, we know the atom is made up of nucleus surrounded by the cloud of electrons. Here one thing we need to notice that the X-ray interacts mainly with the electrons, and it shows a very limited interaction with the nucleus. So we are excluding the interaction with the nucleus. When the incoming X-ray interacts with one electron, it gets diffracted, but it interacts with all the electrons and gets diffracted along the same direction. So we can judge from here that the total scattering from an atom depends on the total number of electrons in it. In other words, it depends upon the atomic number, which we denote by Z. At first glance, it may look like we can simply write the scattering factor, which we denote by F, as Z multiplied by the light scattered from one electron. Say we are having 3 electrons. If Z is 3, so if we calculate the light scattered from one electron and multiply it with 3, we can get the scattering factor. But this is not correct. Why? Because the waves scattered by different electrons are not in phase. What I mean to say that the wave scattered from this electron will be having some phase phi, and the other will be having some phase phi prime. So because of this phase difference, there is the change in the formula of scattering factor, which we write as the ratio of amplitude of X-ray scattered from one atom to the amplitude of X-ray scattered from one electron. So let's now look into it more deeply. To understand this, we will now set up a simple model. Suppose we have one electron placed right at the origin point O, and around this point imagine that the electrons are distributed spherically, forming a symmetric cloud. We can say the radius of this sphere, which is basically an atom, is R. Now let's see what happens when X-ray interacts with this system. If the X-ray beam is incident on the electron at O, making an angle theta, it will scatter with the same angle theta. We represent this incident direction with the n naught cap and the scatter direction with the n cap. So, but the atom does not just have one electron. The rest of the electrons are spread inside this spherical volume. So we will consider a small volume element dV. It also scatters the X-ray in the same way along n cap. Now to describe this geometry properly, we are going to introduce scattering normal vector, which we call it as n vector, and we have derived the expression for n vector in the Lay's equation. I'll just give the summary of that. If this is my incident unit vector and this is the reflected or the scattered X-ray beam direction, we can reproduce our incident unit vector like this, and it's very clearly visible that the angle between n naught and n cap is 2 theta. Now if I join the tip of n naught cap with the tip of n cap, I will get a scattering normal vector, which we call as n vector, and this is what I have represented here on my figure. Also, the magnitude of this n vector comes out to be 2 sine theta, where if we write it in the vector form, it is n cap minus n naught cap. This whole is done in the expression of the Lay's equation.
So taking lambda as wavelength of X-ray and rho the volume charge density, the phase difference between the light scattered from point O, which was actually the electron, and the light scattered from the dV volume is phi r, given by equation 1. Now to calculate the path difference which we are to use in equation 1, we'll have to recall the Lay's derivation where we calculated Lay's equation, and in that the light was scattered from the two different atoms of two consecutive planes like this, and we calculated the path difference by subtracting these two distances, and it came out to be r vector dot n vector, where n was the scattering normal and the angle between r and n is phi. So expanding the dot product, we got rn cos phi, where the magnitude of n is also calculated to be 2 sin theta. In this figure, you can say that this is exactly equivalent to the Lay's equation. So we can use this path difference in the equation of our phase difference, that is equation 1, and we'll get the expression for phase difference to be 2 pi by lambda 2r sin theta cos phi, which comes to be 4 pi by lambda sin theta r cos phi. And to simplify this term, now we will put another variable mu, which is equals to 4 pi by lambda sin theta. Therefore phi r comes out to be mu r cos phi. Let's consider the amplitude of the scattered light from electron and from the whole atom separately. So the light amplitude scattered from point O, which was actually electron, is taken to be the form of A exponential iota kx minus omega t. Here k is actually 2 pi by lambda, and the X-ray which is scattered from the volume dV will be having a number of electrons in that, because electrons are distributed in that volume. So it will be actually the number of electrons in that dV volume multiplied by the amplitude of X-ray scattered from one electron multiplied by the phase, because here the phase plays important role. There is a phase difference between those two scattered lights. So number of electron we have calculated to be rho r dV. Light scattered from electron is already written, and the phase will be exponential of iota phi r. So combining these two, we will get the expression for the scattering factor, which is actually the ratio of amplitude scattered from atom or from dV and the electron, that of electron. But here we will calculate it for dV first. So our expression will be for dF, that is small scattering factor, and putting the expressions that we have already written, the denominator will be that for the electron, and cancelling the common terms, the expression for dF will be rho r dV exponential iota phi r, where phi r is having the expression of mu r cos phi. Now our next target is to find the total F, which will come by the integration of dF over the whole volume of the sphere or the spherical atom that we considered. So we'll proceed with writing the expression of dV in polar spherical coordinates. Why? Because we have taken the spherical symmetry of the electron cloud distribution. So to go with that, I'm just reconstructing my figure again with point O as center. R is the radius at which I have taken the volume element dV. N is the scattering vector. Phi is the angle making with that the n makes with r. D phi will be the small change in the angle. Now the arc length will be r d theta, and the length of radius of this annular ring is r sin phi. Now we will consider that this sphere is made up of series of annular rings which is having thickness of r d phi, and its volume will come out to be circumference of this annular ring multiplied by the width and the thickness. So as I already told you that there is change in the radius, that is r is changing, so there will be a bit of thickness of the annular ring, which we take it as dr, and the width is r d theta phi. dv will be 2 pi r sine phi. So sorry, I mistakenly wrote it d theta, it should be d phi. And then putting the values, we'll get the expression 2 pi r square sine phi dr d phi, which we'll put in the expression of f, and we'll get the double integrand. One integration is on dr and the other one is on the theta. The limit of radius will be from 0 to infinity, and that of the phi will be from 0 to pi. So here yes, there will be the phase term also. Now the highlighted terms in this expression will be used as a stranded integral, which gives the result 2 sine mu r by mu r. So our f will be simplified to 4 pi r square rho r dr sine mu r over mu r. Now for the special case, that is theta equals to 0, mu will be, that is 2 sine theta 0, and sine mu r over mu r with the limit mu going to be 0 will get 1. So hence the expression for f will reduce to 4 pi r square rho r dr, which is actually what? Z, that is total number of electrons in the sphere. So we concluded that f is equals to z for theta equals to 0, and for